I'm going to give a quick status update of where we're at. I'm going to give a little bit of background about the project, what we're trying to accomplish, and I think we've managed to actually do quite a bit since the project started. So I will talk about all that today. So before I get into the actual technical part of it, I do want to recognize that a lot of people have been working on different parts of this project. So at UC Davis, it's myself. I had a PhD student who is now transitioning into a postdoc, and I also had another postdoc now who's on faculty in Poland. So they've all worked on this project in the last 4 or 5 months. Mason Walters, who's sitting in the back of the room there, and I independently were thinking the same thoughts. This really was a coincidence, and Mason called me, and I'm like, we have these problems with column-based connection design, and we're like, no, I agree exactly the same, and we both had actually similar sketches, concept sketches, and so we're like, what, we need to sort of put our minds together and write a proposal for this. So Forel Elsesser has been an industry partner. They are on the peer BIP board, and so there's a pretty strong connection there. Farzin Zarian at UC Irvine has been a collaborator. He's helped with some parts of this. So, and Paul Richards at Brigham Young. And again, there's all these people involved because the peer portion of the project is one part of a fairly comprehensive project looking at column-based connection design in general. Okay, so I'm going to try to first talk about what the big picture is, where the peer part fits in, and what the main or the big goals are. So obviously, I want to acknowledge the sponsors. So peer, AISC and the Charles Pankow Foundation are providing major funding for this project on top of the money that we're getting from peer, and on top of everything else, we also recently got some more money from the California Strong Motion Instrumentation Program, which might help us do some additional validation studies and so forth. So just if you 30,000 foot view, why is this important? Why is this important to peer? Steel moment frames are, they're important generally, but if you think about transportation structures, airports specifically, almost, or rather every single airport, major airport in California on the West Coast has a steel moment frame in it. Like in LAX, San Francisco, Oakland, everything, and that's mainly because you get these large, clear bays, and so these systems are inherently very important to the transportation infrastructure. And people like to think that steel moment frames have been researched, to death, and everybody knows what goes on, and connections in these in moment frames are understood. Turns out that column-based connections in steel moment frames really haven't gotten as much attention in research as one would hope or expect. Okay, so there's still a lot that we don't know about these connections. In fact, there were some tests back in the 70s and 80s, and then about 10 or so years ago, like me and my research group started doing a whole bunch of tests across the street here, and then we sort of built on that. But again, it's more, we still don't know as much about these connections as we do about the others. What that means, basically, again, big picture, is that we actually don't design these connections optimally, and perhaps more importantly, we don't design the system or the frame with proper knowledge of how the connections are going to behave. So we end up like making assumptions, and we end up with system designs that are perhaps either highly unoptimal. In some cases, they might even be unsafe. But so again, we're not sort of doing the best we can to understand how the system and the connection works together. Just a couple of examples of what I mean by that. So for example, the common wisdom is that connections are more brittle than members, and so you want to protect the connection, and so you capacity design the connection to be stronger than the member. And for a column-based connection, you can end up with some pretty absurd base connection designs, because if you have a large column, you want to essentially develop the flanges of the column, right, in yielding. And so, what I'm showing on the top right there is a failure from the OVAT library in 1994 in Northridge. There was, I think, a 4 or 5 inch thick base plate which just fractured, and somebody had to put that gigantic base plate there just because you have to develop that much moment capacity. Sometimes when that becomes completely unreasonable, what people will do is actually embed the column into the footing to try to get more resistance. And what I'm showing there is essentially a picture of an embedment before the concrete was poured, and so you can see that's like a pretty deep embedment. Okay, so all of these things are expensive, painful, problematic, undesirable. Okay, and Mason is nodding there. So this is really painful, I imagine. Anyway, so you've got this picture, okay? So engineers are trying to spend a lot of money to try to make these connections very strong. On the other hand, what we sometimes find, through all the testing that we've done, is these connections are actually pretty darn ductile. Okay, we get like 4, 5, 6, 7% rotation capacity in these connections, and we get these rotations capacities even without necessarily doing anything to make them ductile. And on the other hand, people have been testing steel columns recently, and especially if you have deep columns. Chiaming Wang has tested a bunch, Dimitrios Lignos in Switzerland has tested a few, and the steel columns end up having like all kinds of twisting, lateral torsional buckling, local buckling issues at rotations well below the base connections. Okay, so it's not just that we're actually designing these base connections to be stronger than the column, we're possibly protecting, or we may be protecting in some cases, the more ductile element from the brittle element by making the ductile element stronger. So there's there might be things we're getting backwards. Okay, so we really wanted to take a look and say that, look, can we come up with a system? And when I say a system, I mean, well, can we design these moment frames better, so we don't necessarily have to keep making these connections stronger than the columns? Can we actually come up with a design philosophy of how to design these moment frames with that idea? And then can we actually come up with connections that are reliably ductile, okay, and they're also possibly repairable? So if you think about what all of this entails, it turns out to be a fairly big study, because on the one hand you need to do some physical testing on these connections themselves, just to make sure that you understand their hysteretic response. You calibrate models to reflect that hysteretic response. Then you start putting these models into frame analyses, and then you start running these frame analyses, possibly to get an understanding of the trade-offs between things like the strength of the connection, the deformation demand in the connection, and the performance of the structure. Okay, so very broadly, if I had to just slice the entire body of work that we're doing right now, the money from AISC and the PANCO Foundation is actually going into the component testing. Okay, so we're actually going to be testing a whole bunch of base connections. They're going to be exposed type base connections, embedded type base connections, and there's various details there that we want to check out. The idea is to look at connections that are both ductile as well as connections that are repairable, that we can just kind of perhaps replace a part of and then move on before the next earthquake. So there's like so that's like where the major funding, about like $250K or so, is going just into testing that. Then the peer side of the project is essentially to look at the analysis part of it, at least the frame analysis, because remember, once you have these connections, you're going to calibrate models, and then you want to bring these models to essentially simulate frame performance and see, well, how does the connection interact with the frame, and to try to do that really carefully to understand what could be a beneficial design strategy. And so that's sort of the peer part of it. And then we ended up getting some more money from the strong motion instrumentation program, just because you're coming up with these models for these base connections. Can we get some additional field validation for these? Okay, since we're going to be building a whole bunch of these models and running a lot of these analyses anyway. So that's kind of the big picture. The outcomes, which are all colorful there, I think there's two parts of it. One part of it is just the scientific outcomes, where we think we'd be able to come up with a design method for frames with weak basis, weak and dissipative basis. What does it take? How much rotation capacity do they need? Which has all the good stuff, rigorous consideration of the base and frame interactions, and then obviously details, possibly pre-qualified details for base connections that actually allow you to get this kind of response. And then on a more tangible design documentation or design document level, since AISC is a big part of it, I'm a part of like some of the key committees there. I think the idea is to actually shoot for some code changes with AISC 341 as well as design guide 1, and try to shoot for making sure that we get all of these ideas into practice by about 2022 edition of 341.16, as well as the design guide 1. Okay, so today I'm going to focus on the peer part of it, mainly because this is the peer meeting, but I'll talk about what we propose in the proposal as it pertains to the top left part, and then talk about how far we've gotten there. So this is just a cut paste from the proposal, and this is essentially what sort of a more precise point by point of what we proposed. we wanted to develop and calibrate component hinge models for column-based connections. And then we wanted to actually start doing some nonlinear simulations of frames to understand, or archetype frames with these dissipative bases, to see what the relationships or trade-offs are between the column-based properties, and the kind of design decisions we make. And then start transitioning in from there into coming up with like solid design guidelines, and then developing design examples and so forth. So I think we've sort of made it, I'd say, halfway or a little bit more than halfway in the last 6 months, and mainly because postdocs are an awesome thing. So we're actually pretty happy with where we've gotten. Just to kind of give you an update or a recap of where we are, just a status update. Broadly, we've looked at 2 different kinds of column-based connections: exposed type, and these are the connections where you have the column sits on a base plate, you have anchor rods, and when you have an earthquake, you basically bend your base plate, your anchor rods go up and down, and you get response, you get hysteretic response that looks something like that. It has this flag shape mainly because the axial force tends to recenter your base plate. This is actually a test which we ran over here, I think 2009 or so. So we actually took those tests and we created a model in OpenSeas which kind of tracks that response properly. And again, the idea is to try to make it as quote unquote physically based as possible, so it's not just like a black box hysteretic model that you're trying to fit parameters to, but you have like some understanding of at least the phases or the physical things that are happening on each branch of your hysteresis curve and so forth. Okay, so that's for the exposed type. These are tests that we did at UC Davis, I don't know, like 3 years ago or so, and we similarly created models around those to try to pick up that kind of response. And these are embedded connection tests where you actually have the column going down into a concrete footing. So again, what we've done so far is we've come up with fairly well developed rules and models to capture the hysteretic response of column-based connections that we've tested so far. And then once we have these column-based connection hysteretic models, which we said that we'd sort of calibrate as part of the peer proposals, we can take these and start running parametric system studies to say, well, what happens when you start taking these column-based connection models with different properties and looking at system response. So we've spent, I would say, the last 3 months or 4 months running these kinds of simulations. And just to give you a sense of the kinds of parameters we vary. Now remember, what we're trying to do is we're trying to understand the impact of having weak column bases. Like if we want to design a column base connection which is weaker than what we currently do, what impact does it have on building performance, and what kinds of deformation characteristics does the column base connection need to have to reproduce good performance. So there's a whole bunch of, if you think about the parametric combinations, obviously we've varied the column base strength, and that's the most important variable, which is why I'm focusing on that a little bit. So one is like, the current method of designing these column based connections is you actually design the column based connection for 1.1 RYMP, which is the capacity of the column. Okay, so that's where the column based connection strength is currently. You make it very, very strong. We said, well, what if we design it for an overstrength seismic load, like an omega naught of 3, okay? And it turns out that an overstrength seismic load in many buildings, the base shear corresponding to that sometimes happens, or at least the base or the column base moment corresponding to that sometimes is half or even 1/3 of 1.1 RYMP. So just going from 1.1 RYMP to omega naught equals 3, you're cutting down the moment demand in the column base sometimes by a factor of 2 or more. Okay. Then we tried 2 other sort of scenarios to see whether we could design the column bases for those. One is using an R equals 8, which is to say, well, let's treat the column base connection like a beam column connection, that you're going to actually form like a real plastic hinge there, just as you would get in the beam column connection. See what happens. And then we looked at one intermediate value, which is R equals 3. And for those of you familiar with the AISC code, the R equals 3 corresponds to a situation where you're not doing any special detailing for ductility. You can use an R equals 3 for systems, right? So we just said here are some 4 candidate strength levels for which we could design the column bases, right? And then we had these levels of column base connections. We looked at 4 buildings, 4 through 20 stories. We also looked at the sensitivity to base stiffness. So we did some with like fixed base. We also did some with stiffnesses that were more realistic, what expected values of column base stiffness. And then we started looking at rotation capacities of the column base to say, well, we wanted to see where if you have like 1% rotation capacity, 2, 3, 4, 5, and an infinite rotation capacity, meaning that the column base would never really fail, but you'd actually get collapse of the building because of, say, side sway collapse, mechanisms formed in the beams and the columns itself. So we ran all these, I mean, it took a long time to run, as you can imagine, but again, it was fairly comprehensive parameter set where we were trying to look at the relationships between these three, so these various variables. So I'm going to spend a couple of slides just talking about the results and the broad trends, and again, we've just kind of finished these very recently, so we are still interpreting. I think we've got some good trends, but I just want to show you what we found. So what I'm plotting here is, these are the ones for the realistic stiffness. On the horizontal axis of each graph is the building number of stories. You have 4, 8, 12, and 20. Each graph shows you results for the probabilities of failure / collapse of a building if it were designed, or if the base were designed for an r equals 8, r equals 3, omega naught equals 3, or a 1.1 RYMP. So in other words, if you see this graph here, this is essentially the way these buildings are designed currently, which means every base is designed to be stronger than the column. And if you're in a FEMA P695 type analyses on those buildings, you basically find that your probability of collapse, and this is under an MCE type event, is roughly about 10% or just a little bit more, which is what you would expect, assuming that your buildings have been designed correctly. And then each graph or each bar within that corresponds to a particular rotation capacity. So in other words, if I'm looking at, in this particular case, an 8-storied building, what this is saying is if I designed that 8-storied building, all the bases were designed for an r equals 3, right? Then if that base had a rotation capacity of 1%, the probability of failure in an MCE earthquake is whatever, 100%. You're losing that base because it has a very low rotation capacity. As your rotation capacity increases, you're basically increasing or reducing the probability of failure. So again, what this lets us do is say, well, it lets us probe that if we wanted to have weak or dissipative bases, really what do we end up with in terms of building performance, and what does it mean for the amount of deformation capacity we must have in our structure. So that's sort of the big picture. And just to kind of, before I go further, I do want to point out that if you look at this graph and this, or this this graphic and this graphic here, the actual base moment demand between this one and this one is hugely different. Okay, so the 1.1 RYMP, the bases get designed for a certain moment. If you're designing those bases for an omega naught equals 3, you're designing this bases for about half the moment. Okay, so there's a huge jump in the actual base moment demand, which means that the bases here are a lot cheaper and a lot easier to construct than the bases here. All right, so with that said and done, you can tell right away that those two are non-starters. Okay, so in other words, no matter what rotation capacity you have in the base, no matter what it looks like, maybe there's maybe one stray case here or there which comes down to the 10% acceptable probability of collapse or failure, but other than that, it's basically a non-starter. To say that to designing, no one's going to ever buy designing the base connection for an r equals 8. But what we think, or what we're finding, is by the time you're at omega naught equals 3, you actually do have a fighting chance of getting building response, which is not quite exactly what you have here, but fairly comparable. So for example, you could say that, and especially for the 4-story building, there's no reason to design your base with 1.1 RYMP. You could just design it with omega naught equals 3, which would be a significantly lower force, and you would just be fine. The 8-story is slightly a little bit higher than we'd like, but again, if you look at the 12 and 20-story, it says that if you have about a 4 or 5% rotation, or about a 4 or 5% rotation capacity in your base connection, you could almost get away with designing it for an omega naught equals 3. So in other words, you could just take your buildings the way you're designing them now and design your base connections for a lot lower force, and provided you give them the rotation capacity that you think you need, which is about 4 or 5%, you would be on solid ground. And what we've shown through testing is that getting the rotation capacity of 4 or 5% is actually fairly realistic. In fact, almost all the tests we've done, we've ended up with 4 or 5% capacity or more, even without trying to detail for ductility. So again, if you make that a priority, designing your building down in this region may not entirely be unrealistic. So that's the idea there. So going forward, so this is so we're still going to continue, obviously, to refine our analysis results, do more buildings, make sure under what conditions these findings are valid and so forth, and so that's still going on. But like the big phase of the work now is essentially sort of going to start moving towards testing, and we're still thinking whether we're going to do them at Davis. Amarnath and I have talked about even thinking about doing them here, but the idea would be to actually do these component tests, and these would be on embedded connections as well as exposed type connections, focusing on understanding different details, focusing on understanding dissipative response, focusing on seeing if we can actually make these connections to be more repairable, right? And then once we have those, again, we'd basically try to develop component models for those and try to see how they work within the building, and then finally come up with design strategies. So again, in terms of progress and timeline, I think we've made significant progress with respect to what we set out to do in the proposal, at least as far as the numerical simulations go. We are now starting to think very carefully about planning the experiments. The idea is about mid-2019, we're going to start with the exposed and repairable type-based connections, and then perhaps late 2019, early 2020, we'll go on to the more the bigger embedded type based connections. And then finally, I think I'm done with my tenure as chair in 2020, and I'm hoping to go on sabbatical in 2020, 2021, which is when I'm hoping that I will actually be able to get, spend some time rewriting Design Guide 1 or, working on some design provisions. So that is, that's where we're at. Here's just a picture from one of the previous tests, and a little anecdote to share there. We did a whole bunch of testing here. I don't see Shagzad, but like Don Clyde and Shagzad and I became best buddies. And then for whatever reason, something happened with Nice, and we got kicked out because of some policy, okay? And we already had money from AISC to do testing here, and we didn't have a lab. And it was one of the stories where it's like, my God, what am I going to do now? So it turned out that with the money that we had in the grant, we could actually build a strong floor, okay? So the one thing we do have at Davis is a lot of land. So we dug a hole in the ground, and actually Shagzad and Don helped me, figure out how to build a strong floor. So we built this about maybe 5, 6 years ago, and we did these tests, okay? But it was just a lot of fun to build that. And like I said, so maybe we'll use that strong floor again, maybe we'll come back, we don't know, but the idea is to do some more of these tests. So yeah, that's all I had, and I'm happy to discuss any part of this. Yeah.
One question I had is how much the three-dimensional response affects the response of this connection. You should be doing tests in 2D, and then of course your models are all these little relatively simple springs that all move in the plane, but buildings move in 3D.
Yes.
So whether you have restraints or not restraints, you're going to have rotations at the base and things like that. So do you have any sense?
So I have so many times asked for money to do tests on 3D. People so far haven't, but we've done continuum finite element simulations on these. What it turns out happening, okay, is that if you're looking at an exposed type connection, your capacity, because you're actually sharing anchor rods in both directions, you actually do end up diminishing your capacity a little bit, not hugely, and that is a factor. That is a factor. For embedded connections, it's less of an issue, mainly because the actual parts of the connection that are failing in the two different directions are not actually the same parts of the connection, because you're actually trying to crush concrete in one direction versus you're crushing concrete on the other side of the column. So my sense is, based on the finite element simulations, that we could be off by about 15-20% just in terms of the base strength if we don't account for that interaction. But unfortunately, we haven't ever gotten the money to be able to do those.
So you don't have things like, you don't see problems like low cycle fatigue of the anchor. I don't know exactly how you figure out these connections, but there is also steel involved.
So the thing is, if we yes, no. So okay. So if you it depends on exactly what the detail is. If you have an exposed type connection with anchor rods in there, the predominant mode of yielding is either the plate bending or the anchor rod going under cyclic loading. The thing is, because you're not technically either buckling or localizing in the anchor rod, just from an absolute standpoint, the strains in the anchor rod are usually not high enough to cause low cycle fatigue or fracture before you reach a very, very high drift in the column, just as a matter of order of magnitude. In the embedded case, predominantly it's the concrete failing. And typically, if you have like biaxial bending, then in one direction you're crushing concrete ahead of the flange, and in the other direction you're actually crushing concrete ahead of the web in this direction. And so they don't seem to interact that much, at least in the finite element models, which yeah. So, but no, it's a factor. Okay, so right now nobody knows what nobody knows what the exact answer is to that. Yeah. Yeah.
So in the motivation for the project and then the project title, you talk about airports and long span or long clear distances, but then the analytical models you showed were 4, 8, 20-story, pretty closely spaced column buildings. How do you see the results you have here translating towards the goal of the project for
so these are
structure?
Yeah, so we do plan to do more buildings or airport structures at some point to do some simulation. So right now we want to get baseline understanding of, is this real, can this happen, and we wanted to get some feel for that, which is why we used the buildings that we had.
Yeah. I mean, how do you see these results translating into those structures? Different characteristics, I assume. How is
so okay, so the thing is, like, so airports are lower rise structures. In terms of the actual clear spans, like our 4-story frame isn't significantly different than what you would have in an airport, for example. And so if you look at, I'm just trying to show where this is. So I think it's like a 30-something foot span in the airport, and I think our 4-story frame is actually pretty consistent with what you might have there. And for that, we actually find that the effect of having the weaker bases is the least detrimental. Yeah.
Any other questions?
Yeah.
The grout, you said that you create a grout that you need between your column and the how critical do you think it is? I mean, have you paid attention to it for damage and
So yes, so the way, yes. So for example, what would happen is if you get typical non-shrink grout, you're putting it in the base plate, it's about like 8, 9 KSI, and we actually test those. If you look at the concrete under the grout, it's about 4 KSI, but the difference is what ends up happening usually is that the grout is unconfined and the concrete is confined because the grout's sitting. So what we found is, depending on what the strength is, what confinement you have, you can actually replace the capacity of the grout by an effective strength, and you actually design your base plate so that your grout or concrete never really actually breaks or fractures. So you want it to be controlled by either the plate or the rod. Okay.
Thank you.
Sure.